Hello everyone, my name is Emma Jane and I'm part of the training webinar team here at Hardent. I'd like to start by welcoming you all to our webinar on the Xilinx Vitis software platform. We're pleased to have so many of you take the time to join us online this afternoon. Our presenter today is Reg Zatrapolik. Reg will present for about 50 minutes and then he'll take 10 minutes at the end of the webinar to answer your questions. This is a great chance to ask him about the Vitis tools, and you can submit your questions to us at any time during the webinar using the questions box. If we don't have the time to get to your question today, you can expect an email response from the training team in the next few days. I hope you'll all enjoy the webinar, and I'll now pass over to Reg to begin.
Good afternoon, everyone, and welcome to our Get Ready to Use the Xilinx Vitis Software Platform webinar. So I'll just start off by giving you a quick introduction to Hardent and let you know who we are and some of the activities that we do, and then we'll dive into the material. So Hardent is located in Montreal, Canada. We are a design services, training, and IP company. So we're a Xilinx Certified Alliance Program Partner, which means for any Xilinx designs, we are certified by Xilinx to perform those designs, and have been a training partner since about 2009. So we provide training for on webinars for worldwide, online for worldwide, and in person for most of the Eastern US and all of Canada. So we've got a fairly broad territory. Myself, my name, as Emma Jane mentioned, is Reg Zatrapolik. I'm based in Ottawa, Canada, and I've been with Hardent since 2009. Previous to that, I had 13 years of experience as a Xilinx FAE and DSP specialist, and design experience 10 years as a designer doing telecom network design, asset management product design, and military avionics cockpit display design, so mainly video systems for avionics. I was voted the outstanding instructor for North America in 2017, 18, 19, and 2021. So I'm going to be your presenter for the next hour as we talk about the Vitis IDE tool and the software platform. So Vitis is based on the Eclipse open source framework. It's an evolution or a migration from the previous embedded tool, which was known as SDK. Vitis has some extensions to the Eclipse framework. So that allows you to customize the environment, allows all of the back-end tools to be integrated within the platform, and allows some other features like debugging tools and other hardware generation and productivity tools. We'll see what some of those tools are as we go through our description. So Vitis provides you with the complete tool chain from the front end right through the back end. So the front end is what we consider to be the user-facing tool. So we call that the editor. We'll get into a little bit of a description on what's involved there in just a minute. The back end is all of your Makefile tool chain. So your compiler, your assembler, your linker and loader, ultimately allowing you to create the load file or the binary file that you'll boot your system from. So the editor will include things like your code editor for editing your C and C++ code, tools and utilities to manage your project, menus to navigate through your project, all of the dialog boxes for error navigation and debugging, all of the controls to select the various build options, debug options, profiling options, everything you need to create, manage, debug, and analyze your project. Now, the interaction from a user standpoint is via either text editors or application wizards, which we'll talk about just a little bit later as well. The backend tool is all of your Makefile tool chain. So Makefile is going to run the basic tool chain, and that all happens via the graphic interface that's provided within the Vitis development environment. So we start off with the C compiler. Your code will compile down to assembly code. From there, the assembler will run, creating the machine code or the object code. The link loader will then run to resolve all of the unresolved symbols that are in memory and produce for you the ELF file, which will then allow you to boot each of the processors in your system. Now, many of you may be familiar with the previous generation, which we knew as SDK, the Software Development Kit. So you might be concerned with migrating from SDK to Vitis. You might be wondering just what are the differences and what are the challenges that you're going to encounter as you go through that migration. So let's take a quick look at that. SDK was a very, very flat project hierarchy. So it had all of the capabilities for managing projects that target Xilinx devices, but each project, each application that you had was managed effectively as an individual task or individual project targeting a specific processor resource within your system. And that worked very well for simple systems where we didn't have to have a lot of intercommunication between the applications or between the processors. But as our systems start to get more and more complex, as we start getting more and more concurrency, we start getting challenges with debugging and profiling and communicating between the different applications or different processes that are running. It's also not clear exactly how each of the application gets loaded from directly within the SDK workspace structure. Vitis provides you with the ability to handle multiple workflows that are based on your design and on your system. Now, if you're familiar with SDK, the migration to Vitis is going to be pretty straightforward. You'll find that the project presents itself a little bit differently. We manage the project a little bit differently. Some of the buttons move, some of the displays change a little bit, but in terms of the flow, fundamentally, it's pretty much the same thing for each project that you're developing. What Vitis changes is your board support package is no longer a unique entity. It now is integrated into the domains, which provides you with a much improved hierarchy. It's much more clear in Vitis to understand how the process is going to boot, how various applications get loaded onto each of their processor, and we also have an easy setup for debug where we can understand the concurrency within our project. So if we have multiple applications that are running on different processors simultaneously, that's clear within the Vitis framework that we'll see. Now, one of the big changes you'll find in Vitis is we don't automatically generate a multitude of reports. And that's done intentionally to keep things a little bit cleaner. So we have limited information that's presented. And in order to generate those reports, you're going to find it's often a two-step process, where first we have to enable the report to be generated, and then we actually have to invoke that report in order to generate it. So that's going to streamline the flow, it'll speed up the tool, and it'll simplify the clutter when you're running your Vitis designs. So let's take a look at how we would go about developing our application. We'll find there are 3 steps to this process. The first step is pretty well a planning stage, where as a system architect, step number 1 is going to involve selecting the family, identifying your performance and power requirements, and the behavior of the system. Once we've specified exactly how the system will be laid out and which processors you're going to target within your Xilinx devices, the next step is to identify the hardware. So that's step 2 down here, and that's going to be done through the Vivado IP integrator. So within IP integrator, we'll define our hardware description, we'll identify all of the peripherals, we'll identify the memory map, and we'll include any IP that we have that might run in programmable logic, or perhaps we might have some custom IP or some Xilinx IP that we want to include within our project. That will then be exported to Vitis, and Vitis is going to be step 3 over here. That's our software development flow. So within Vitis, we'll identify the OS, we'll create the application, we'll actually code it up, we'll export from the Vivado IP integrator a description of our IP, so any RTL or programmable logic components that we may have within our system. We'll integrate all of those with our software component. We have testing, profiling, validation, and debugging utilities that are built right into the Vitis platform. And then, of course, we'll package everything up. And finally, we'll take the ELF file from Vitis, combine that with the bit file or our programming bit stream from Vivado, we'll integrate those together for deployment on our target platform. Now, again, there are a couple of things you're going to find different as we go through the Vitis flow. Vitis includes predefined hardware platforms for Xilinx boards. So if you're targeting any of the Xilinx supplied eval or demo platforms, these are already built right into Vitis. All you need to do is select them from the drop-down menus, and you can target those boards without any additional configuration or hassle. If you have your own board, you can create your own description file of that hardware that would then get exported from Vivado IP Integrator to the Vitis tool. We also have an emulator built right into Vitis. We actually use something called QEMU, which you may be familiar with, and that allows you to do your software development before you actually have completed your hardware design and build. So if you want to get an early start on software development, we have a path to do that. Now, the hardware description that we've spoken about that we're exporting right in this step is going to be exported as an XSA file. That stands for a Xilinx Support Archive. Again, if you're familiar with the SDK flow, you would probably recognize this as the HDF file, which was the hardware description file that we used to export from SDK. So that's been changed now. I'm going to export the XSA file instead. Same purpose, different name to identify that it's a different structure from what we had previous. We'll then build the platform project, build your application, compile all your code, and generate the boot file. So your software development is going to start after we've exported a description of our hardware. We'll take another look at this process with a little bit more detail a little bit later on. Now, again, going back in history, we look at the SDK Project Structure that we had in the previous generation tool. And what we see again is a very flat structure. So each application is built on a specific processor. We would have our hardware specification that was exported here again as an HDF file, a hardware description file, and then we would go about coding up or programming all of the various components of the application. So might be standalone applications, might be real-time applications, could be something where we were targeting a soft processor like Microblaze running in the programmable logic. We might have Linux applications that are running. And of course, we're going to need a first stage bootloader to boot the system, and we may have PMU firmware that's going to handle platform and power management. So with this flat structure, we have the ability to build all of these bits of software and firmware code and identify the processor that they're loading on. But what we lack is the insight or the visualization of how these processes might communicate with each other and how we go about booting the system. So which processor loads first or boots first? Which application loads first? Is there a strict order to loading them? Do they load all at once? Are we running everything concurrently? Are we running one application and then another? Are there options in which applications load for any given boot that we may run? That's all not very clear from this flattened structure. And so we have these questions that get raised. How do the applications communicate? What applications are working together? Which applications are just on, let's call it standby, where they're perhaps not loaded right from boot? How do we debug the system? Is there one application or one processor that comes up first and then loads the other? Is there something that we need to pay particular attention to when we're doing our performance analysis and our profiling? And of course, again, how does the system boot? So the reality is a little bit different from what the SDK simplified flattened hierarchy would lead you to believe. Now, if we look at Vitis, we find that Vitis has support for multiple platforms, multiple project types, multiple applications running concurrently. Again, it's based on the Eclipse open source integrated design environment, or GUI. Everything is Java-based, so that means it runs on both Windows and Linux, and it does support all of the embedded software application development that you would have been familiar with from SDK, but it does a whole lot more than that. So in terms of the user standpoint, if you're a traditional SDK user, then running Vitis is really just buttons are going to change. The way that the tool presents your projects is going to change a little bit, but you'll still be quite comfortable compiling your design, developing your applications, and loading your OS using the Vitis platform. If you're at a higher level of abstraction, developing system or software developers that are looking for application acceleration, leveraging the programmable logic resources or the other resources that you find within the Xilinx devices. Perhaps you want to take advantage of the AI engines that's in the new Versal parts, then you don't have to have a detailed knowledge of the underlying hardware and of things like VHDL or Verilog or how to integrate RTL accelerators with your software. A lot of that has been automated and streamlined. So for the software developer that's working at that higher level, we have what we call Xilinx software acceleration flow provided via something called the Vitis application acceleration flow. And so that will streamline the development and acceleration of your applications using scripts that are built right into the tool flow. Now, everything can be run via the GUI, via the Integrated Design Environment or IDE. It can also be run from the command line. So if you're using something like TensorFlow or Caffe and you want to include the Vitis tool chain in that tool flow, then that can all be integrated via the command line scripted flow. So it gives you a lot of options depending what level you're developing at and what your final needs or target is going to be in terms of both your tool flow and your target device. So you find this higher level of integration really extends the capabilities of Vitis, regardless of whether you're building an application that's going to run locally, what we call edge application, or something running in the cloud. So if you're doing a domain-specific development using more abstract tools, the Vitis libraries and tools will integrate directly into that via the command line flow. If you're a traditional, what we call legacy embedded developer that's used SDK in the past, or if you just want to do an embedded software or firmware development, then Vitis will also give you that capability. In order to handle all of this additional acceleration, I mentioned earlier that you don't have to have a detailed, in-depth knowledge of the programmable logic or the architecture or the AI engine. Of course, it's useful if you do understand it. You'll get better utilization and better performance, but even if you don't, that can get abstracted away and leveraged by taking advantage of the Vitis accelerated libraries that are provided by Xilinx and by Xilinx partners. Now, in order to invoke this acceleration, we use something called the Vitis runtime environment. We talk about that in more detail in a course that we offered called Vitis Excel, which is the course on how to build accelerated kernels via this integrated flow within the Vitis tool. So that will allow us to leverage Vitis in order to target these elements with our Vitis target platform. It's quite a comprehensive tool and really quite an advantage over what SDK used to give us. There's a much higher level of abstraction if you are looking for it in dealing with the Vitis tool. It also makes it easier to use some of the underlying hardware components like the programmable logic and the AI engines without having a detailed knowledge of RTL, VHDL, Verilog, and integration through the Vivado tool. That all gets scripted and that environment gets provided for you. Now, we mentioned earlier that there are extensions to the standard Eclipse framework. And so these extensions provide you with utilities like your first stage and second stage bootloaders to boot the entire system. Platform management software, or what you may know as PMU firmware, can also be included, modified, and developed through the Vitis platform, as well as your applications, your OSs, and any other configuration component that you want to target or leverage on your Xilinx targets. So all of the make files to run the tool chain are all automatically generated. The acceleration tool chain to build and integrate the accelerator kernels. Can also be scripted and automatically generated and integrated within this flow. So there are processors and accelerator kernels that are supported both within what we call the PS, the processor system, and the PL or fabric, which we refer to as the programmable logic or the programmable fabric in the embedded components that Xilinx provides. Other features that we have within the Vitis IDE, we focus on that full platform support. So it's everything from your OS development to your actual application development, the bootloaders, the platform management firmware, all of the interprocessor communication. That's all comprehensive, all integrated within the Vitis platform. The way that the tool presents all of this information is by organizing everything into separate projects. Now, again, the information that gets presented is limited. So what we mean by that is we're not automatically generating a multitude of reports. Once again, if you're familiar with SDK, you would have found that when you run any compile or any build on your application, there are a lot of reports that get automatically generated. Under the Vitis tool, because we're running so much concurrency, and you'll see that in just a minute, we didn't want to overburden the user or clutter the environment. And so many of the reports only get generated when you as a user specifically request that information. Once again, that's often a two-step process. First, you need to enable the report, then you need to go generate it. So it cleans up the whole flow. It also speeds up the tool as it's running. So let's take a look at a little bit more detail on how you would go about developing your application. So assuming that we've already done the system architecture step, we've selected our target processor, we've decided what components are going to be built in software, what's going to be in hardware, what's going to run on the programmable logic or the AI engines, what we're going to have within the Xilinx device and external to the device. So all the partitioning and target exercises have been done. Now we get into the hardware definition stage. So this is where we're running Vivado, and we're running under the IP integrator tool. We're leveraging IP that we may have, targeting perhaps programmable logic or elements that might target the AI engine, or maybe bits of our source code that we want to use for various interfaces. So we combine all of that through IP integrator. And again, that can include RTL, so VHDL or Verilog, could include other IP, could even include DSP components that we've built through System Generator and used MATLAB to run our analysis on those components. So once we've created the hardware definition, we've identified the memory map, we've identified the peripherals within our system, we've done all of the debug in the programmable logic, so that's all Vivado exercise. Then we export that. Remember, that's going to be our XSA file that we have here. Whoops, sorry, wrong arrow. We export that up here to Vitis. Now we import into Vitis, we define the platform, and that's where we go about doing all of our software development. So we go ahead, we develop the application, we define the interfaces to the accelerator kernels that we've created over here, where we want to do some hardware acceleration, and then we download that to hardware, to our board, or we can run that in emulation mode. So maybe we haven't completely built all of our hardware and we just want to run an emulation of the hardware in order to fast track the software development while the hardware is still being finalized. We can go through a complete debug of our hardware, our software, and we have the utility to do co-simulations and co-debug between hardware applications, or sorry, hardware kernels and software applications. So again, that's built right into the Vitis platform. Ultimately, we want to combine the hardware bit stream with the software execution ELF file and load those onto the board. So that will be the final step. And typically we'll do this after we've done all of our software debug, our hardware simulation and debug, and our emulation to make sure that everything is at that highest degree of functionality before we actually go about targeting the board. So the starting point is going to be all of the hardware, either custom hardware that you've built or predefined hardware from Xilinx. We specify it with the XSA file, and that then becomes part of our platform project, and that's where we go ahead and develop the software. Now, when we're developing the software within Vitis, the steps are going to be first create a workspace. And the workspace is really just a big directory management structure. So once we've defined what all of the various projects are going to be in software and set up that directory structure, we go about defining the platform project. And the platform project is going to have both a hardware and a software component. The hardware component is the hardware description of the underlying target hardware. The software component is going to be what we call the domain. And that domain will identify the target processor, perhaps the OS, the board support package, the peripheral components, the memory components that we've got within our system. And then from there, we develop the application, and all of the boot components automatically get generated for all of those entities. The application development is simply the process of writing the code. We have templates that will accelerate the coding. So it starts off with simple things like hello world, and then there are a number of other templates that can be used for application acceleration and other sorts of tasks or development examples that you might want to leverage. Again, next step, download everything. And you've got a couple of choices when you're downloading to the hardware. You can download through JTAG and use the Vitis environment as a debug environment, or you can create a boot image, a flash boot image. You can load your boot flash, boot from that flash, and still monitor the activity via the Vitis interface in order to do things like hardware, software, code debug, and system profiling. So again, Vitis is going to provide you with all of those capabilities. When we get into the debug stage, we have the ability within Vitis to debug multiple applications running on multiple processors simultaneously. And so that's a big step beyond where the previous generation, the SDK tool, used to take us. We can do profiling to make sure that our timing specification has been met. If it hasn't been met, then there are various degrees that we can expand the profile and get more detail to identify exactly where those bottlenecks may be. So again, much more comprehensive tools integrated completely within the Vitis platform. Now, as you're working with these projects in Vitis, everything starts off by defining the workspace. And so the workspace, as I mentioned, is really just what does the directory structure look like for all of the projects that we're going to build. Now here, we've got a kind of a simplified view where we're just showing you the platform project and the system project, but we'll build on this and we'll show you how we can have multiple projects within one system, all supported within Vitis. So the platform project is going to have three components to it. It'll have a hardware component, which is our hardware specification, again, specifying the active processors, the peripherals, the memory map. The software component will identify the domain. So this domain could be an OS, it could be a target processor if we're running standalone or bare metal, could be an R5 if we're running an RPU, if we're running an RTOS. So there are lots of different options on just what the domain will identify. And then the third component is going to be firmware with our FSBL and our PMU firmware. Now, all of these combine together to form the platform project. The hardware specification is provided by the XSA file, the Xilinx system architecture file that we exported from Vivado IP Integrator, excuse me. So this is where our XSA file comes into play. The software component, again, identifies the domain or the OS, also identifies the drivers that are required to support any of the hardware components specified within the XSA file. Once again, we could have multiple software domains on a single hardware specification. So we'll show you an elaborated view in just a minute that describes that a little bit better. And if we make any changes to the hardware, we need to re-import the XSA file and rebuild the platform project to reflect those changes. Now, the boot components, the firmware that we mentioned over here, is going to consist of your FSBL, your first stage bootloader, and any platform management firmware. So this is the PMU firmware, which is going to be optional within your system. You must have a first stage bootloader. PMU firmware is optional. Xilinx provides you with a PMU firmware template that can then be modified and also provides you with an automatically generated FSBL. So this process is really not difficult. If you want to do any customization of either the FSBL or the PMU firmware, it's simple text files. It's all editable within the Vitis environment. So it's a fairly easy thing once you understand it to do any customization that you might require. The next step is our system project, where we're going to actually develop the application. So the system project is going to group applications that run simultaneously. Again, here we've got a rather simplified view where we're only showing you one standalone application targeting a single A53 APU, but we'll expand on this in just a few minutes. So the application project is going to be based on the domain, which we identified up here in our platform project. Remember, the domain is either going to be the target processor or the OS. We'll explain just what that means in just a minute. Now, the way everything is presented to you with all of these various projects is via a fairly simplified GUI. So within Vitis, we've got four main areas in the GUI. There's the Explorer area that we see up here, the project settings and build area that we have right here, the assistant down here, and then the information area with the console and all of our logs and additional information down here. We also have different perspectives that you can run. So you'll notice up here in the right-hand corner, right now we're in the debug perspective. There are three perspectives that are included with the tool. So something we call the design perspective, where most of your code development and design work will be done, the debug perspective, which quite obviously is for debugging, and then we have a performance analysis perspective. If you want to see different information, different reports, then you actually have the ability to create your own perspective with your own windows or views of information. Again, the GUI is simplified. The Explorer perspective gives us all of the project folders, the source files, the build files, and the reports that get generated for each of the applications. The Assistant view is going to provide us with all of our project management utilities. So this is where we would go about changing the project settings, enabling various reports, generating reports or reading reports that we might have generated, building our project, running the applications, and launching the analyzer. So that's all done from this assistant view that we see in the lower left corner. The project editor is going to display all of the different views for various objects to change settings, to change the target platform, to change the build configuration, or to specify things like the hardware functions that might be running in programmable logic or in the AI engine, for example. It also allows us to edit any of the project settings that we have within our system. And then finally, the console is where we get all of our build messages, our warnings, our errors, all the project properties, the logs. If we want to launch a terminal that connects to either the emulation or to the actual embedded design running on hardware, we'll see that in a terminal view that we can have within the console that we have right here. Now, let's expand on our projects a little bit. So we know that the workspace is really just going to separate everything into directories. So that's going to identify all of the projects that we have within our system. And we remembered that we had three things. We had our platform project, our system project, and then the application within the system project. So the platform project, once again, has three components to it. It's got the hardware specification. So again, this is the XSA file that defines the processors, the memory elements, the memory map, the peripheral elements, all of the hardware components within our system. The domains are right here. And within a domain, we'll be able to edit our target processor. We define whether we're running standalone or bare metal or an OS like Linux will be referenced as a domain. And then the system projects are going to be used to group together all of the applications that run simultaneously. So the platform project then will be a container for the hardware platform, as we just mentioned, for the processor settings. So when we define the domain, we're actually going to define the processor settings, the firmware component that we mentioned earlier for the bootloader from the first stage bootloader, and any PMU firmware that we may want to have in our system is defined as part of the platform project. And so again, we can have multiple domains within our platform because we know within the Xilinx devices, we have multiple processor core resources. We have up to 4 APU cores, 2 RPU cores, and if you're familiar with the Versal parts, we also have AI engine cores that we can target with our code. And we, in addition to that, we may have some programmable logic kernels within our code. So when we're working with these projects, the system project will represent all of the applications that are running simultaneously. So let's say we have a standalone application here running on our first APU, a second standalone application running on a separate APU. So 2 standalone applications within a system project must run on different processor targets. All of the applications within the system project are going to run simultaneously. So that allows us to group together and quickly see which applications are running concurrently or simultaneously. If we have a different application that might be swapped in or booted or loaded on any given processor, that will appear within its own project. So here we have a second project with a different application that's going to run on our RPU here. So we could not run application 1 on the R5 RPU at the same time as application 2 on the R5 RPU because they're within different projects. So that's not going to be supported. Now, the only way that we can have multiple applications targeting a single processor resource is if we're running under Linux. Linux is a symmetric multiprocessing OS, so that can manage the allocation of resources for multiple applications targeting one or more individual processors within our system. So again, multiple projects cannot run simultaneously. Any applications that we want to run simultaneously must be within the same project. And if we're standalone, bare metal, or RTOS, they must target different processor resources. So that's probably the biggest difference between how SDK represents your project and how your project is managed and referenced in Vitis. So we've got this ability to see that concurrency, and that's a big advantage when we have these more complex systems that we're trying to build with multiple applications, multiple OSs, all running concurrently, targeting different resources within our system. Other aspects of our application process, so we've got the hardware specification. Again, that's going to define exactly what the hardware resources look like, we have to have at least one hardware specification. If we have different options for enabling different hardware and peripheral elements, we may have different hardware specifications that we want to be able to load in different Vitis workspaces. The board support package still exists. The board support package is going to indicate all of the functions that support hardware. Now, the difference between the XSA file, the hardware specification, and the BSP file, your board support package, is that the hardware specification will identify all of the hardware that exists in the system. So it's basically going to be every memory element, every peripheral element, everything that contains, that occupies part of the overall address space. So if it exists, it has to be identified in the hardware specification in the XSA file. The board support package, on the other hand, identifies all of the drivers and libraries that need to be loaded and included when you boot your system. So if you're not using a particular hardware peripheral, you don't need the driver for it, you don't need the libraries to support it, your boot image will then be smaller if you leave out those elements that aren't required, so you can reduce the size of your boot image by not including those components within the board support package. So we see the board support package is actually going to represent a subset of all of the hardware that exists within the hardware specification. And then we go ahead and build the application project. So the application project gets built on top of the BSP. It has only one domain at a time, again with the caveat, unless you're running a Linux OS, and that allows you to create the domain where you'll do all of your testing, your debugging, your profiling, and ultimately your deployment and delivery. Now, within Vitis, we have different perspectives, different views, different editors, and so the perspective is going to give you access to all of the profiling utilities, debug utilities, and it will help you reduce the clutter by allowing you to focus on the task at hand. If you're doing code development, then you'll do what we call the design. You'll be in the design perspective or the C++ perspective. Now within Vitis, we support both C and C++ languages. In fact, you can even do mixed mode if you want to. The debug perspective is going to have all of the views and capabilities for setting watch points, break points, controlling your code execution. So that will give you all of the options that you need to debug your system. And then, as we mentioned, we also have an analysis perspective that will allow you to do performance analysis and profiling of your system. Now, in order to control the compilation, we need to run the tool chain. Eclipse as a framework doesn't have a tool chain. What we do with Vitis is by default, we include the GNU tool chain. Now it is open, so if you want to replace that tool chain with your own, with something else, with Microsoft Visual Studio, for example, you can replace it. You simply need to make sure that whatever tool chain you choose to replace it with is licensed and targeted within the Vitis environment. The tool chain is going to provide you a well-defined path through the tools, and so you need to provide the correct files at each stage. So in the initial stage, we'll take in our source code, and again, it can be mixed C and C++. Of course, we recommend C++ as being the best, most efficient, most comprehensive variant. Add in your compiler options that will describe exactly how the code is going to be compiled and what optimizations you want to leverage. And from there, we run the compiler. Now, the compiler is going to produce assembly code. So the next stage of the tool chain is going to be to run the assembler that will take that assembly code and turn it into a binary format object code. At this point, when we come out of the assembler, our symbols and addresses may be unresolved. So we need to run the linker, which is going to look for all of these unresolved calls. If it's a library function, it'll connect that code with the library. Anything that's unreferenced will be flagged as an error. Libraries are going to be all of the C libraries and user libraries that exist as pre-compiled programs and functions. These could also be accelerators. The linker script is then going to add a level of control to identify exactly where the various code segments and data elements get stored. So we've got multiple memory elements within our Xilinx devices, and for performance reasons or management reasons or security reasons, you may want to map various variables and code segments, data and code segments, into different predefined areas. Now you can hand code the linker script. That's a fairly difficult task if you're not familiar with linker script management. So Xilinx provides you with a linker script wizard that simplifies that process. And then ultimately, we need to produce the ELF file, which is going to be our executable and loadable format file that we'll use to boot the system. Now again, Vitis provides you with multiple configurations. So let's talk about what the difference is between some of these configurations. We'll start off with the debug configuration or debug that we get from the debug perspective. So what the debug configuration does is it allows us to debug our program. Now, we may want to debug it running on the target hardware, we may want to debug it in emulation mode before we've completed the target hardware. So the debug configuration is going to have all of the settings, and it's going to produce our code for compilation through the tool chain with no optimization. And what that means is, as we're single stepping through our code, each element, each code word or function will occur unaltered. So we won't optimize anything out. We'll give visibility of all of the variables, all of the memory contents. You can peek and poke or read and write or modify any element. And of course, you can set all of your standard debugging tools to single step, set breakpoints, step over, step into. That's all available through each individual step of your source code. So it produces an ELF file that we'll use, that will load onto our target processor or run in emulation, again, with no optimization. So software debugging, that's a critical aspect. The debugger that we use within Vitis is going to be either the GNU debugger or the system debugger. The system debugger is a little bit more advanced, a little bit more comprehensive. It uses something called TCF, that's the Target Communication Framework, which you interface to via JTAG. And so that's going to support debugging of all of your applications, whether they're standalone or Linux, your Linux kernel, your first stage bootloader, your PMU firmware, all of your concurrent operating multi-core systems that you may have with multiple applications and multiple OSs running in your system. So it's, again, very elegant debugger included within Vitis. The next configuration we're going to look at is the release configuration. So the difference between the debug configuration and the release configuration is the release configuration contains all of the compiler optimizations. So all of your settings that you've identified within the tool chain are provided, and this is going to be your highest level of optimization that you'll get for your final released code that will go to your production deployment. And we also have a profile configuration. And what the profile configuration does is it adds in the ability to create graphs and tables to illustrate or view all of the profiling of the performance of the application. So you can identify any bottlenecks, whether they're within the software code itself or running any accelerator kernels. We can look at exactly how long the data takes to move from the processor to an accelerator kernel, how long the accelerator kernel takes to run in programmable logic or in the AI engine, and do all kinds of what if and analysis scenarios using the profiling configuration. So again, it adds in some extra components that you won't find in the debug configuration or the release configuration. Now, ultimately, we need to boot the system. So we need to have a boot file to do that, and the Vitis tool will also generate for you the boot file. So the initial configuration is done via the configuration wizard, and this is actually part of Vivado IP Integrator. This will produce a register initialization file, which is part of the first stage bootloader. So as an absolute minimum to boot your system, you must have a first stage bootloader. Now again, Xilinx provides you with the first stage bootloader automatically, also provides you with a template that you can use to modify any of the first stage bootload code or include other functionality within the first stage bootloader. Everything after that is optional. So you may choose to have a second stage bootloader if you're loading something like Linux. You may choose to load your bitstream as part of your boot file image. You may choose to have platform management or PMU firmware in your system to manage power or interprocessor communication or other functions and utilities. You may have one or more OSs that you want to load. You may decide you want a hypervisor. You may be running secure code using ARM Trust firmware, and you may decide that you want a golden image or a fallback image should you have a boot failure. So these are all optional sections that can be included in your flash boot image. We're not going to go into the details of all of these in this forum. We do have courses and extensive Xilinx documentation that describes all of these other components. So in order to migrate from the SDK tool to the Vitis tool, it's actually a fairly straightforward process. First thing you do, you take your SDK project and you upgrade your hardware specification. So that's going to produce for you your XSA file from Vivado IP Integrator. Check your IP status, make sure it's all compatible. Once you've got everything set up, you export the hardware and export your bitstream from Vivado into Vitis. Now we can go into Vitis, we can import the XSA file, so you can do it pretty well from either side once it's been produced. Import the SDK project into Vitis, so the project that you used to have that you were working with in SDK can be imported, and you can import that either by selecting the workspace or you can import it as a zip file. After your import is successful, you update the hardware specification. You do that by right-clicking on the platform project, and you simply say, update hardware spec. That will then generate for you the updated hardware. At that point, you go into Vitis, you build the platform project, you rebuild the application project, you rerun your simulations, your emulations, your debugging if required, your profiling if required. So again, the migration, from SDK to Vitis is a fairly easy to navigate push button flow through the Vitis tool. Now there is, as I mentioned, extensive documentation to support this. There are documents on the Vitis platform on migrating from SDK to Vitis as a step-by-step guide that we see right here. There's information on embedded design and creating your embedded design, including tutorials. There's lots of information on the command line tools and the runtime environment. And if you have questions, there are forums that allow you to enter all of your questions and post those to the Xilinx community. In addition to this, there are lots and lots of training courses that you can follow to assist you with understanding the Vitis tool and understanding all of the flows and capabilities of the Vitis tool. We also have a number of other webinars that will extend beyond the simple introduction that we've had today, take you a little bit deeper. So there's a webinar that we have that looks at the Versal ACAP device. I'll actually be presenting that in just about a month on September 13th. The webpage to sign up for any of these webinars is open right now. If you go to our website, hardent.com/training, you'll find the registration webpage for each of these webinars. There's another one on faster timing closure for your programmable logic This is presented by my colleague, Rick Eggleton, who also spent about 15 years as a Xilinx FAE previous to his career at Hardent. And then we have a boot and configuration webinar that's coming up in a couple of months in October that I'll be presenting that looks a little bit closer at the MPSoC boot and configuration process and requirements. Again, I mentioned we have lots of training courses. So in addition to the webinars, we have 2- and 3-day training courses that include hands-on labs that cover pretty well every aspect of Xilinx design. So we see our programmable logic path right here at the top with constraints, time enclosure, and productivity for programmable logic. We have architecture courses that cover all of the Xilinx components, including the embedded components, the RF SoC components, and the Versal components that we see down here. Courses on the AI engine, software and embedded courses, or course stream that we see through here. The level 1, 2, 3. Level 2 is kind of your getting started course. Level 1 is your basic languages. Level 2 is your getting started courses. Level 3 is kind of an intermediate level course for people that perhaps have some experience with Xilinx tools, either current or previous. And then level 4, this gets us into our power user or advanced courses. Now the color coding, in case you're wondering about that, is all identified by the key that we have down here in the lower right. So anything that we see in this blue or teal color is a standard Xilinx course that you'll find described on the Xilinx website. Everything we see in red is a course that we've developed exclusively at Hardent. You won't find anyone else that offers this course, but you will be able to take this course either online or hopefully in the near future live from us from Hardent. So that just gives us a better understanding of the learning path and course descriptions. If you want a description of any of these courses, you can go to the Xilinx website and we've got a detailed description of each of these courses if there's anything that catches your interest or that you'd like more information on. Now, in terms of the scheduled upcoming training courses that we have, the one that might be of most interest is our Migrating to Vitis workshop that we have scheduled for August 26th and again October 26th. And then we've got the embedded system design courses right below where this is a Hardent exclusive course where we look at the MPSoC architecture in a lot more detail. And as we mentioned, we've got the Vitis acceleration course, which is going to be offered August 18 and 19, and again, August 4 and 5. Now, there are a lot of other courses that are scheduled. So once again, if you want more detail on the schedule or any of the courses, feel free to go to our website. You'll find all of that information. You'll also find an email link where if you have a request for additional information, you can send an email and get that additional information. So that's everything I wanted to present in this seminar. We're going to open everything up for questions. So we'll have about 5 or 10 minutes where we can answer any questions that might come up. And once you close your webinar, you'll find a quick survey pops up. So if anybody does have any additional questions afterwards, then feel free to either send those via the survey or any questions we don't get answered, we can email to you afterwards. I want to thank everybody for attending, and let me just look at the questions here and we'll see if there's anything that we need to answer right away. Okay, now for some reason, bear with me for a second. There we go. Okay, so we've got a few questions. First one, is PetaLinux integrated into the Vitis environment? And the answer to that is yes and no. So the PetaLinux tool chain is not integrated into Vitis. You need to run that as a separate tool chain via the PetaLinux tools, which is a command line tool currently. But once you've generated the Linux kernel, you can import the Linux kernel into Vitis and do your application development within Vitis. So you can't build the kernel within Vitis, but you can build your application on that kernel from within Vitis. That also will enable you to do all of your debug and profiling of your application and your Linux kernel within the Vitis environment. So that's why I said yes and no. You have to build the kernel separately. Once it's built, you can use the Vitis tool to do all the rest of the application development, debug, and profiling. Another question, what about ATF secure and non-secure mode? Yeah, very good question. So there are a few options when you're building your OS and your software. Within the Xilinx environment, we do support ARM Trust Zone firmware. So that's the acronym for that is ATF. Now, when you're running ARM Trust Zone firmware, there are a couple of options. You can run either a secure boot or a non-secure boot. And you can also have the ability to identify specific memory and peripheral apertures as protected. So that's all done through the Xilinx Memory Protection Unit and Peripheral Protection Unit, which is a hardware-enforced, software-controlled mechanism that's built into the MPSoC, the Zinc UltraScale Plus device. So all of that is supported within the tools, within the device, and within Vitis. So there is ARM Trust Zone firmware. There are ARM Trust Zone firmware templates that are provided by Xilinx. The ability to define the memory and peripheral protected apertures is provided within Vitis. The ability to provide to generate secure protected peripherals is included within the Vivado tool, and the ability to define secure and non-secure OSs and applications is provided within Vitis. So all of that is supported and provided within the environment. Third question, can you run ATF secure and non-secure application? Absolutely. You can run it, you can emulate it, you can debug it. Again, all fully supported within the Xilinx toolchain, within the MPSoC device, and within the environment. You can't find any documentation on ATF configurations. So that may be because you need to first register for the Secure Lounge. Now, there are secure libraries that are provided from Xilinx. And I'm not sure if all of the documentation is on the public side or if you first need to register for the lounge. I have full access to it and I have everything bookmarked. So I can assure you that the documentation exists. I can't remember offhand whether I had to register through the lounge to get that documentation or whether it was somewhere on the public side. The easiest way to find that is post a request on the Xilinx forum. And the Xilinx forum is monitored not only by the user community, but also by Xilinx. And so they'll be able to direct you to either the lounge or the document that you're looking for. And Xilinx forums generally have a fairly quick turnaround. It's often within minutes of you posting a question. So if you go to the Xilinx website, look for the support page, and then go into the forums, post your question for ATF documentation there. You should get a pretty well an instant response on that. Any other questions? Okay, so it looks like that's all the questions we have for today. Again, I want to say thanks to everybody for attending. I hope you found this information useful, and I would encourage anyone to attend a future webinar or any training course that we have listed. Again, you can find all of those registrations on our webpage at www.hardent.com.